We will now start to talk a little bit more about what we can do with multiplets. So we've already learned about the splitting patterns associated with hydrogens based on their neighbors. And we know that this is all based on the n+1 rule, which states that the number of hydrogens, which are the neighbor to a resonating hydrogen, will be split by that number plus 1. So what we can do, though, is we can extend this out a bit, and we can say that the distance between those peaks, so for example a doublet or a triplet, what we can do is we can determine the distance between those peaks, and then from that information pull out even more. And that is what we're going to be talking about for a good chunk of today's lecture, which is that the distance between the peaks of a multiplet provide further information about a proton and its neighbors, and it's referred to as the coupling constant and is often given the abbreviation of J. So if we take an example, if we have, let's say, a doublet, okay, so this is a doublet associated with a proton, and let's say the peaks come out at 1.55 and 1.50. The distance between those two peaks, as you can see, is 0.05 ppm. And what we can do is we can take that distance and multiply it by the magnet strength. All right, and so the magnet strength is specific for every different magnet has a different magnet strength. Typically, they come in varieties of 300, 400, or 500. So if we imagine that this is done on a 300 megahertz NMR, what we're going to be doing is we're going to be calculating this. This is 0.5 ppm, and remember that's in parts per million of the megahertz. So we're talking about hertz over megahertz for our ppm, and we multiply that by our magnet strength, which is 300 megahertz. The megahertz cancel out, and what you get to is a coupling constant that is measured in hertz. And so in this case, what we'd find is that the coupling constant was 15. So 0.5 times 300 is 15 hertz. And we also, because we are multiplying by the magnet strength, we're actually kind of canceling out that factor. So the coupling constant is independent of the magnet strength. All right, so it doesn't matter what magnet you do it on, what the magnetic field is, the coupling constant is always the same. And so that is also how you would calculate coupling constant. You would measure the ppm difference and then multiply by the magnet strength. And so what we get is a whole series of coupling constants. Now, these coupling constants vary based on the types of hydrogen interactions that we can measure. And so when you're dealing with, let's say, a hydrogen-hydrogen interaction from an alkane, or carbon-carbons next to each other, notice it says free rotation. That coupling constant is usually around 7 hertz. So that's typical for, let's say, an alkane. When you start looking at hydrogens that are on an alkene, this is where we get a lot of information. So if we're talking about a cis double bond, what we see is the coupling constant is around 10 hertz. If it's trans, then that's a 15 coupling constant, 15 hertz. So you can very easily differentiate a cis from a trans double bond by proton NMR. If the two hydrogens are on the same carbon, all right, and so we talked a little bit about this before in lecture, at least we should have. If you have two hydrogens here, they're on the same carbon, but they are not chemically equivalent because this hydrogen is cis to the methyl, whereas this hydrogen is trans to the methyl. So those hydrogens are different. If they're different, they'll couple to each other. But the coupling constant is small, around 2 hertz. Aromatic rings, typically, they have coupling constants around 8. Usually these can vary, plus or minus 1. So they could be up at 9, down at 7, but typically around 8 for coupling constants. What's also unusual is that you sometimes get coupling between hydrogens that are not adjacent on an aromatic ring. It is a tiny coupling, but it can be there, and it's usually 2 hertz. Finally, one of the last coupling constants is this, what we call allylic coupling. And so what you see here is you have a hydrogen on an alkene, and it has an adjacent hydrogen, but that's on, let's say, an alkyl group. Typically, those coupling constants are around 6. Another example of, let's say, something like an allylic coupling would be this type of coupling, where a hydrogen on an aldehyde is adjacent to a hydrogen on CH2. This also usually falls around 6 hertz, but they can vary from molecule to molecule, but typically around 6. So we've seen some of these. We might have seen this example in class, but again, what you can do is you can actually measure out the coupling constants for certain structures. And so let's say we take a look at this compound right here. If we're looking at the carbon-carbon coupling on the alkene, if you notice, this is a cis double bond inside the ring, and so we would anticipate it being a 10 hertz coupling. If you actually did the calculation on these guys, what you would find is it's about 10 hertz. I would provide you with the chemical shift that you would need, then you could calculate your own coupling constant. Again, down here we have a trans double bond, and if you did the measurements, you would see that the coupling on those two hydrogens is around 15 hertz. So we're going to move on to the concept of complex splitting. All right, and so when we talk about complex splitting, we're talking about different hydrogens coupling one hydrogen coupling to two different non-equivalent or non-similar coupling hydrogens. And so what you have to do is we take an example of styrene here. And so if we have, let's say, although it's tiny, but we say we have HA here. HA is going to be coupling to HC because that's the cis hydrogen, and HB as well. That's the trans hydrogen. And we already know that HA, the coupling constant to HA to HB is 15 hertz, or it should be 15 hertz. And so you get this 15 hertz coupling from HA coupled to HB. So HB is split into two, or HA is split into two by HB. But HA also couples to HC, and that coupling constant is about 10 hertz. So I'm kind of off scale here, but you can imagine, there we go, that this distance is about 10 hertz. And so the reason why it's called complex splitting is because one proton coupled to two different hydrogens will result in two doublets. This is often referred to as a doublet of doublets. And so if we actually look in the NMR spectrum, I'm going to actually blow this up for a second so you can see it. The doublet of doublets, kind of hard to see here, but here we go. That is clearly not a quartet. There's no symmetry within that. But if you actually calculate the coupling constants for 1 to 2 and then 1 to 3, what you'd find is you'd get a 10 and a 15 hertz coupling constant. All right. The same thing is true for if you looked at HC. HC is going to have a coupling to HA. All right. So HC will couple to HA. It will also couple to HB, so that will also be a doublet of doublets. So this is a more complicated topic, but something that you need to be aware of. So again, if we look at this, if we're breaking it down, basically in this slide, they're just doing what I did before, which is looking at, you kind of say HA, it's split. And now in this case, instead of 15, it's 17, but it's still your trans coupling constant. Then the cis coupling constant is 11, and so what you see is the doublet of doublets. This is the case for hydrogens that are different. If we take a look at, let's say, these two hydrogens here coupling to the methyl as well as to the hydrogens over here, yes, the CH2 and the CH3 are chemically different, but what is the coupling constant for this CH2 to this CH2? It's around 7 hertz. What is the coupling constant for the CH2 to the CH3? It's about 7 hertz. Since the coupling constants are the same, your coupling is going to look simple. And so that's why this is going to end up being a sextet, because you have 3, 4, 5, and it's simple splitting, so it would be 6 peaks. The diastereotopic protons, that starts to get more into complex splitting. And so what I'd like to do is kind of go over diastereotopic protons again and talk about how we can see these as complex splitting as well. So we talked in class about the fact that since we have a chiral center here, the two hydrogens that are adjacent to that chiral center are not going to be the same chemically. They are in chemically different environments at all times. Therefore, these two hydrogens are not the same. So if they're not the same, they will couple to each other. So these two will couple to each other as well as to the hydrogen here. So if we label, let's say, this one hydrogen 1, hydrogen 1 is going to couple to hydrogen 2, and it turns out this coupling constant tends to be very large. They can be up around 20 hertz, and so let's say 1 is 18 hertz. All right, then besides that coupling, it will also couple to the adjacent hydrogen over here. And so that will couple. And that's about 7 hertz because that's your alkyl coupling. And so again, what you'll often see for one hydrogen on this carbon, you're talking about a doublet of doublets. So this is why it gets really complex. H1 will be a doublet of doublets. H2 will be a doublet of doublets. And this H over here is going to couple to the two different protons. It might end up looking simple, and we do see that there. It ends up looking kind of simple because the coupling constants between those two will be similar. But you get very complicated signals just for 3 protons on a simple molecule. I'd like to finish talking about one more concept, which is the idea of exchangeable protons. So anytime you have a proton on an NH2, or let's say a nitrogen, or an oxygen, typically in a deuterated solvent, we talked about that before, if we should have, if we didn't, basically when you run your NMR, you want to run them in solvents that do not contain protons. So if we want to use, let's say, chloroform as an NMR solvent, we will replace that hydrogen with a deuterium. And so now this is excellent as a solvent because it doesn't show up in proton NMR. But what happens oftentimes is that these signals on NHs and OHs can become exchanged. And what you get is deuterium replacing hydrogen. When you do that, this doesn't show up. What happens is often in many solvents that exchange is slow. And so what happens is you do still see a peak, but it's very broad. And so exchangeable signals turn out to be broad, or they disappear depending on the solvent. We'll talk more about this in class, but certain solvents you'll see it disappear completely, such as D2O, which has a fast exchange rate. Other solvents, such as CD3, acetone D6, these will have very slow exchanges, and you might actually see a sharp signal for your alcohol. So this finishes up the proton NMR lectures, and we'll talk more in depth about some of these concepts in class.